To hit a bullet with another bullet is a feat of engineering. To do it at 5 times the speed of sound is a miracle of mathematics. This is a deep dive into the predictive algorithms that power the world's most advanced air defenses. Welcome to Kinetic Chess. Seriously, we begin with the fundamental reality of hypersonic flight. A missile traveling at Mach 5 is moving at approximately 1,715 meters per second. At this velocity, the air itself ceases to behave like a fluid and begins to act like a solid obstacle. This is the regime of aerothermodynamics, where the friction between the air and the missile's skin generates temperatures exceeding 2,000 degrees Celsius, hot enough to melt steel.
Seriously, but the heat is only the first problem. The real challenge lies in the geometry of interception. To understand why intercepting a Mach 5 missile is considered impossible, we must look at the closing velocity. When an interceptor and a target head toward each other, their combined speeds can exceed 3,000 meters per second. This leaves the guidance computer with a margin of error measured not in meters, but in centimeters, and a reaction time measured in microseconds.
For decades, missile defense relied on proximity fusing, the idea that you only needed to get close enough to blow the target up with a shrapnel cloud. But at hypersonic speeds, proximity is not enough. The energy involved is so vast that even a minor deflection can result in a miss. Modern systems have transitioned to hit-to-kill technology. This is the Kinetic Kill Vehicle, or KKV. It carries no explosives. It destroys its target through the sheer force of impact, using the kinetic energy formula, 1/2 mass times velocity squared. At these speeds, a small piece of tungsten hitting a warhead has more destructive power than several hundred pounds of TNT. To achieve this, the interceptor must perform a series of calculations known as proportional navigation. At its core, proportional navigation, or ProNav, is a guidance law that dictates that the interceptor's rate of turn should be proportional to the rate of change of the line of sight to the target. If the angle between the interceptor and the target remains constant, they are on a collision course. Seriously, but a Mach 5 missile isn't just flying in a straight line. Modern re-entry vehicles are capable of non-ballistic trajectories. They skip off the atmosphere like a stone across a pond. This is where the mathematics of the Kalman filter enters the fray. Named after Rudolf Kalman, this algorithm is a mathematical tool that uses a series of measurements observed over time, containing statistical noise and other inaccuracies, to produce estimates of unknown variables. In our case, the Kalman filter predicts where the missile will be 5 seconds from now by constantly updating its belief about the target's current velocity and position. Seriously, the sensor suite is the eyes of this operation. We start with early warning satellites using infrared sensors to detect the massive heat signature of a missile launch. Once the missile enters the mid-course phase, ground-based X-band radars take over. These radars operate at high frequencies, allowing them to distinguish between a warhead and a cloud of decoys.
Seriously! However, the radar horizon is a physical limit. Because the Earth is curved, a ground-based radar cannot see a low-flying hypersonic cruise missile until it's dangerously close. To solve this, we use the Cooperative Engagement Capability, or CEC. This allows a destroyer at sea to share its radar data with a battery on land, effectively seeing over the horizon.
Urgent. As the interceptor approaches the target, it enters the terminal phase. Here, it can no longer rely on ground-based radar due to the latency of the signal. It must wake up its own internal seeker, usually an active millimeter wave radar or an uncooled infrared imaging seeker. Seriously, but here physics throws another curveball, the plasma sheath. At Mach 5 and above, the air in front of the missile becomes ionized, creating a shroud of plasma that can block radio waves. Thoughtfully, engineers must design sensors that can see through this fire or position them in areas of the airframe where the plasma is thinnest.
Once the target is locked, the Divert and Attitude Control System, or DAX, takes over. Traditional missiles use fins to steer, but in the thin upper atmosphere or at high Mach numbers, fins are either useless or would be ripped off by the force of the air. The DAX uses small rocket thrusters located around the center of gravity of the kill vehicle. These thrusters fire in millisecond bursts, shifting the interceptor laterally with incredible precision. This is kinetic chess at its most literal. Each move by the target is countered by a microburst of thrust from the interceptor.
Urgent. The final 100 milliseconds are a blur of computation. The onboard computer is processing gigabytes of sensor data, calculating the exact point of impact on the target's airframe, ideally the sweet spot where the warhead is located. When the collision happens, the energy release is equivalent to a localized earthquake. The two objects do not merely break, they atomize. This entire process, from launch to impact, is the culmination of a century of progress in aerodynamics, material science, and computational theory. We have moved from the era of simple ballistics to an era where the battlefield is defined by the speed of light and the precision of the algorithm. As missiles get faster and more maneuverable, the math must get smarter. The impossible physics of today will become the standard engineering of tomorrow, as the shield continues its eternal race against the sword.